nos va a hablar sobre Deep Learning y Kung Fu. Un aplauso.
Okay, good morning. This is quite funny because I recently graduated from here, from this school, and I've been in your position several times, a lot of times. And I had the privilege to sit down in those seats to watch amazing talks by amazing speakers, and also trivial talks by boring speakers. And I think this one is going to be one of the second. So, because, for example, this is just clickbait, and I'm not going to talk about Kung Fu at all. This is just, I'm a liar. And also, I'm going to follow the first law of presentations, that live demos always work in presentations. So that's what I'm going to do. I'm going to start with a demo, which is here. Okay. Okay. We are seeing myself and several points around my eyes and around my nose, the ears, the shoulders. So I'm going to close this because this takes a lot of resources. But what is happening here? Let's get back to the presentation. What was that? What was happening there? So imagine that the laptop was a black box. It's a black box and is reading input frames from the webcam and doing some processing and returning some sort of skeletons that represent the state of the people in the image. And by state, I mean a more detailed information about people than just a bounding box. So we're going to call this state, these skeletons, human poses. And we're going to call this problem human pose estimation. Now, human pose estimation has a lot of applications. Just imagine yourself doing this and watching how the door closes, or just trying up new clothes without having to go to the shop, just using your smartphone, or just raising your hand to stop a self-driving taxi. Or eventually, you could build a robot that beats you at a Kung Fu battle. And well, even though it has a lot of applications, we're not seeing these applications because this problem was not seen as possible, as solvable, until just a couple of years ago, when deep learning, with the emergence of deep learning, and also with the gathering and development of huge data sets and well-defined data sets, like, for example, the COCO key points data set. The COCO key points dataset just describes each person in an image with not only one body part or two body parts, 3 or 4, but 18 body parts. So to solve the problem, you could say, okay, let's stack just a lot of hundreds of convolutional layers, and just keeping in mind that the last layer has to be 18 matrices, where each matrix is a heat map, and where each pixel in those heat maps, each pixel value represents the likelihood of that pixel to be a specific body part. For example, the right eye, the neck, the left shoulder. So, but that's cool, but there's a problem. Because what happens when we have multiple people in the image? How do you know which part belongs to which person? So this is where OpenPose enters the game. OpenPose is a deep learning model developed by the Carnegie Mellon University, and it was trained not only with the 18 body parts of the COCO dataset, but also with the connections between them. The 19 connections between them. There are 17 meaningful connections and 2 more non-meaningful connections. And with all these, what you get is a deep learning model that outputs the 18 heat maps, but also it outputs 2 more matrices for each connection. Why 2 matrices? Because you have information of the direction in the x-axis for each possible connection, and also you have another matrix giving you the direction of in the y-axis for each possible connection. And we call this part affinity fields. And we're going to use these part affinity fields to score each possible connections between the detected body parts in the heat maps. So we're going to do some post-processing here, and after all, we're going to get those skeletons. Now, if we want to shed some light into the black box of OpenPose, we see that the first 10 layers are just the first 10 layers of the BGG feature structure, fine-tuned. The next layers are what we call the first stage, which is divided in 2 levels. The first level is outputs the heat maps, and the lower level outputs the part affinity fields. Now, if we want to make this more complex and more accurate, we can stack another stage, another more complex stage. And if we want to make this even more complex, we can repeat this second stage again to have a third stage, and we can repeat it again to have a fourth stage, and again, T times. We can make this as complex as we want. Now, I come from a robotics background. If you show me this, I could say, okay, that's amazing. That's very cool, but can I use it? And you can say, okay, yes, you could use it if you have a GPU like this big, that it's not going to fit in your robot, and it's going to consume your battery in 2 seconds. You could also use your CPU, but it's going to last forever for each frame. So, that's a problem not only for me, but for every person involved in production or even or Android developers. So this is important. So how can we make this network less expensive, less computationally expensive, and faster? Well, the solution is removing or reducing operations. So that's what we're going to do. We're going to make this faster. So first step to make this faster is realizing that that is a convolutional layer, that also is a convolutional layer, that also is a convolutional layer, and every layer in the network is a convolutional layer, which makes this network a fully convolutional network. That means that we can choose the size of our input image. And for if we have a smaller input image, the kernel has to slide fewer times. Wow. Fewer times, and we reduce the operations if we choose a smaller input image. We can also reduce the operations if we just stack 2 stages instead of, say, 7. And finally, we can, this is the trickiest way to reduce the operations. You can, instead of using standard convolutions, because standard convolutions take into account all the channels in the input tensor. Instead of that, you can have different kernels. Each kernel just taking into account one different channel, and then merging all of these outputs of the kernels with the point-wise operations. And doing this change from a standard convolution to depth-wise plus point-wise convolution, you could reduce almost k-squared operations, where k is the size of the kernel. And this is the trickiest because you need to retrain your network. And I have to thank this guy here, Il-Do Kim, that did this for us. He retrained this network in a depth-wise convolutional fashion. And well, now we have all the tools for making this as fast and as expensive as we want for our application. So that's what we're going to do. We're going to play with these parameters. And here, okay, now in this Jupyter notebook, we're going to use 2 graphs. One graph is going to be as usual, the standard open pose, and the second one is going to be the open pose with the depth-wise convolutions. So here we see that it takes like almost five seconds using the standard open pose with BGG for each frame. We can see here how this this slide here is gonna select the part that we want to see. And if we change the input image, this K parameter is gonna reduce the input image. We reduce it to, say, half, for example, or 60%. We're gonna see that instead of 5 seconds, we come with 2 seconds. But the accuracy reduces. If we take like 10%, let's try, 10% of the input image size, we see that we can just see nothing here. And if we, instead of using 4 stages, we use more stages, we can see that the accuracy is better, but it also takes more time. It's thinking, 8 seconds, but the accuracy is great here. We also can see that if we change between BGG to mobile where it takes depth-wise convolution, we see that the time reduces drastically. We can see here that we just have half a second with our image that is even bigger than usual. We can have 2 frames per second here. And if we reduce the image, we see that this goes reducing and reducing until we also reduce accuracy, but yes, depends on your application. And if I have more time, we can also see, because we are showing here the heat maps, but if we show the part affinity fields, we can see the differences between the X matrix and the Y matrix. Here in the X matrix, you see that in the neck connection, this is positive and this is negative because the two men are watching opposite sides. But if we take the Y path, we see that those have the same direction, the same sign. Okay, that's all. And finally, I have applied this here in a lab that it's just in one of those buildings. To my bachelor thesis, and this works very well, and they're still using it. But it could be very cool. Now people are making very cool things using GANs that you can not only have 2D information, but also 3D information with just an RGB camera. I have to say also that I'm using ROS, and with ROS you are obliged to use Python 2, which there is not very well. Now we have ROS 2 that I have not tested it, but it seems that with ROS 2 you can use Python 3, so I'm gonna give it a try. And well, that's all. Thank you.
Any question?
Hi, thank you and congratulations for the talk. As you were showing, it took a second to 10 seconds up to 8 seconds to process a single image. How could you use I would like, for example, to follow a ballet. So for example, I have filming the session, but it's continuous in the sense that you can have the person is moving in a concrete way and goes, the point is following a path. How would you be able to get this fact that you can find the path to improve the performance and have it in almost real time?
Okay, thank you for the question. You have several options. One is using a neural network with a memory that traces the last frames to try to just learn the usual movements of ballet. Or also you can use maybe Kalman filters to try to estimate probabilistically the path that the person is going to take. I think that using Kalman filters, you're going to take it's going to be cheaper. It's going to be also faster than using neural networks with memory that tends to be slower.
Any other question?
Thank you.